Welcome all. My name is Suresh, lecturer in ECE. I'm going to teach the subject electronic devices and circuits. In that, today's topic is tuned amplifiers. In the previous lessons, we have discussed about the power amplifiers. That is class A power amplifier with resistive load. We have seen the efficiency derivation and class A power amplifier with the transformer load and class B push-pull amplifier and also class B complementary symmetry push-pull amplifier along with the derivation of the efficiency. Now today's topic is tuned amplifiers. First, classification of tuned amplifiers. Tuned amplifiers may be classified into two categories, that is small signal tuned amplifiers and large signal tuned amplifiers. Small signal tuned amplifiers amplify small signals at radio frequencies. As power involved is small, these amplifiers are operated under class A operation. Hence, the distortion is negligibly small. On the other hand, large signal tuned amplifiers amplify large signals at radio frequencies. As power involved is large, these amplifiers are operated under class B or under class C operation. Hence, distortion is large. See here, classification is based on either it is small signal or large signal. Small, large, depending on the input power of the signal. Input, how much is the voltage, how much is the power of the input signal. For the case of small signal, we have small power involved and it will be tuned at radio frequencies. And for the small signal tuned amplifiers, we should use class A operation, because if you use the high power signals, there is dissipation is more, power dissipation is more in case of class A, and power is wasted, and the efficiency is maximum 25% for resistive load. So the circuit may damage if you use the high power signal, that is large signal, as input. And the distortion is negligibly small. Why? Because in the class A operation, the conduction angle theta is 360 degrees. That is, there is no loss of input signal, that is, there is no distortion in the output, that the shape of the input is preserved as it is in the output. That's why the distortion is negligibly small. For the large signal amplifiers, the efficiency should be high, because less power has to be wasted and less power dissipation is also there. So we go for the class B operation, in which the theta, the conduction angle, is only 180 degrees, that is either positive half cycle or negative half cycle. But the tuned circuit itself eliminated most of the harmonic distortion. What are harmonic distortions? Harmonic distortion means if there is a input signal with frequency f, in the output there may be a possibility of multiplication of these frequencies will appear, multiple frequencies, that is the n multiples, the numbers 1 into n, 2 into n, 3 into n, so 3 into f, 4 into f, like that. Those type of frequencies may appear in the output. Those type of frequencies are called harmonic frequencies of the input signal, which are undesirable. We need only the f value, that is whatever the input frequency is there, it has to be get at the output. Because of some non-linear distortions, non-linear characteristics in the circuit, we can get this harmonic distortion, but they are not desirable, they are unwanted signals, they has to be eliminated. Next, classification of small signal tuned amplifiers. First, we have seen the classification of tuned amplifiers in which small signal and large signal. Now we are looking into the classification of small signal tuned amplifiers. It is usually required to use a number of tuned amplifier stages in cascade in order to obtain large overall gain. Right? To get the maximum gain and higher gain, we use if we use only the single stage, that may not be sufficient. So we should use multiple stages. These cascade tuned amplifiers may be put into the following three categories, that is single tune, double tune and stagger tuned amplifiers. We will see why these amplifiers are called single tune, double tune and stagger tune in the next slide. That is, single tune amplifiers uses one parallel tuned circuit as the load impedance in each stage, and all these tuned circuits in different stages are tuned to the same frequency. Right? We use multiple tuned circuits in cascade to get the overall large gain in these three types of tuned amplifiers. But in particular single tuned amplifier, though we have each parallel circuit, each tuned circuit in the load of particular circuit, but they all parallel circuits are tuned to the same frequency. Double tuned amplifier. In case of double tuned amplifier, we use two inductively coupled tuned circuits per stage. See, observe here, per stage, per circuit stage, we use two inductively coupled tuned circuits. So both the tuned circuits being tuned to the same frequency. We use the two inductively coupled tuned circuits in this double tuned amplifier. For stagger tuned amplifier, we use a number of single tuned stages, single tuned stages in cascade. The successive tuned circuits being tuned to slightly different frequencies. The stagger tuned. In case of stagger tune, we have single tuned stages in cascade connection, but all the connections are not tuned to the same frequency, slightly different successive tuned circuits are being tuned to slightly different frequencies. Now see the introduction about single tuned amplifier. A single tuned amplifier is one in which one parallel parallel inductor in parallel with the capacitor, that is a tuned circuit, that is also called tank circuit, TANK, tank circuit, is used as a load for the amplifier. In case of single tuned amplifier, you can remember the basic amplifier circuit. In that, if you remove the load resistor and replace it with a tuned circuit, that is inductor in parallel with the capacitor, it will become single tuned amplifier circuit. And if you can remember the frequency response of that particular single stage amplifier with RC coupling, which is very flat and constant gain in the bandwidth, that is in the mid frequency range. But if you remember the same basic amplifier with a transformer load, you can see in the frequency response there is a bump. That means there is a sudden increase in the gain at a particular frequency, that is F0, that is resonant frequency. The same concept applied here. We replace the resistive load with tank circuit, that is inductor in with capacitor, which will act as a tank circuit, which will act as a tuned circuit. Right? In that case, the frequency response curve is a resonant frequency curve, which we are going to be discussed in the further slides. So the circuit of a single tuned amplifier is shown in the figure, and voltage gain of single stage transistor amplifier is given by So this is a single tuned amplifier circuit. See that same as basic amplifier, but the load resistor RL is replaced by L in parallel with capacitor. Observe that capacitor is a variable capacitor. C is a variable capacitor because the tuning can be changed. The resonant frequency can be changed by changing this value of capacitor. We can see that in the operation topic. Now just see the introduction, that is voltage gain is beta into RL by Rn. The AC load resistance of tuned circuit, that is parallel LC circuit, is given by RL is equal to ZP, that is L by RC. Therefore the voltage gain of a tuned amplifier is given by AV is equal to beta into Z parallel by R input. The frequency response, you see the frequency response, the maximum voltage gain occurred at a particular frequency f0. After f0 and before f0, there is a steep decrease in the voltage gain. The resonant frequency of parallel LC circuit f0 is given by f0 is equal to 1 by 2 pi root LC. This is the formula for the frequency response. We can calculate the f0 if we given the values of L and C, right? At the resonant frequency, the impedance of the parallel resonant circuit is very high and it decreases as the frequency changes above or below the resonant frequency. The parallel impedance, the impedance is the important concept in this case of tank circuit, right? We can get this f0 is equal to 1 by 2 pi root LC formula from the impedance calculation. If we calculate the parallel impedance from the circuit and at particular frequency f0, if we consider f0, substitute the f by f0 in that impedance equation, and if it is assigned equal to 0, that means the equation is assigned equal to 0, that means the real part, actually the real part, sorry, it's not the real part, it is the imaginary part of that impedance, that is the reactance component from the parallel LC circuit. If the parallel impedance, if we calculate the parallel impedance, that is XC in parallel with XL, X is 1 by omega C and XL is omega L, right? And if the parallel impedance, we have actually two components here, resistance and reactance. Though the resistance part here is 0, but the reactance part, X part, we take common as X and we apply the omega values and assign that particular reactance to 0, that is when it will become 0 at a particular frequency f, that is called f0, the resonant frequency. If you want to calculate the resonant frequency formula, you should assign that imaginary part, that is the reactance part, to 0, then you will get the equation f0 is equal to 1 by 2 pi root L C. So at the resonant frequency, the impedance of the parallel circuit is very high and it decreases as the frequency changes above or below the resonant frequency. Therefore, the voltage gain of tuned amplifier is very high at resonant frequency. The gain from the frequency response curve, you can see the gain become maximum at f0. However, the above and below the resonant frequency, the voltage gain decreases rapidly. Higher the Q of the circuit, the faster the gain drops off on either side of the resonance. This is the quality point, Q point, so quality factor, Q factor, which can be calculated from the even equation, right? That can be discussed in the further topics. No need to go into the particular details. Only we have to learn about the circuit operation. Single tuned amplifier circuit. Observe the circuit as you are very familiar with the circuit. from the starting of these video lessons electronic device and circuit. From the very first lesson on July 2nd, we have discussed about the basic amplifier circuit in the CE mode, common emitter mode. Same circuit present here also, but only the difference is the load resistor is replaced with a tank circuit, that is a inductor in parallel with the capacitor. Figure shows a circuit of a single tuned amplifier. In figure, the output is taken with the help of capacitive coupling, where in figure the output is obtained by inductive coupling. Figure 3.23. In this, we can see the output is taken across the inductor. The output is taken and with the help of inductive coupling, concept of inductive coupling. Similarly, we can take the output in the figure 3.22, the capacitive coupling. We have taken across the capacitor. Output is taken across the capacitor. The signal to be amplified is applied between the base and emitter. Between the base and emitter, the input signal Vs is applied. R1 and R2 and Re fix up the and stabilize the operating point. Already we know these points. C is the bypass capacitor. Emitter capacitor will act as the bypass capacitor or shunt capacitance for the Re. A tuned circuit consists of L and capacitance C acts as a collector load. A tuned circuit consisting of L and C in parallel will act as collector load. C is generally variable, so that the resonant frequency of the circuit may be adjusted. We can also use a variable inductor, right? This is important because from the formula F naught is equal to 1 by 2 pi root LC, where L and C are the inductor value and capacitive value. If any of the value is changed, the F naught will change. So here in this circuit we have used the variable capacitor, and similarly we can use variable inductor also, and both inductor and capacitor both can be variable, and both variable inductor and capacitors can be used in a single circuit also. Thus the values of the capacitance and inductance of a tuned circuits are adjusted in such a way that its resonant frequency equal to the frequency applied of the applied signal to be amplified. So whatever the input signal we are applying AC, the same frequency to the same frequency of the input signal, the tank circuit has to be tuned so that we can get the maximum gain at that particular frequency. Next, circuit operation. The high frequency signal to be amplified is applied between base and collector. The value of C of tuned circuit is changed such that the resonant frequency becomes equal to the frequency of the signal. At resonant frequency, the tuned circuit offers very high impedance to the signal frequency, and thus large output appears across it. If the signal is complex, that is consisting of many frequencies, this is important, then the frequency corresponding to resonant frequency will be amplified. Other frequencies will be rejected by the tuned circuit. That's how the radio receivers generally work, because in the air, from the air and from the transmitting station, there are different channels, different stations, different FM or AM stations will transmit different signals. But when you are using a receiver, that is radio receiver. We have to tune to particular frequency to which a channel that we want to listen, right? By adjusting some knob on the receiver, by changing some, by turning some operation, some particular knob on the device, we are actually tuning to the coming signals, input coming signals. That is, we are changing the C and L values and we are tuning to the desired frequency. Whenever the frequency matches with the input coming signal, then the maximum gain will occur and the output will be a amplified version of the desired signal. If the signal is complex, this is the practical application, right? So the tuned amplifier selects and amplifies the desired frequency. So it selects and amplifies the desired frequency, both operations it will do. So this is inductive coupling of the same circuit. Now we have to go for the double tuned amplifier circuit. Observe the circuit. This is same as the single tuned amplifier circuit, but with tank circuit extra tank circuit connected across the load, that is tank circuit, first tank circuit L1 and C1 and second tank circuit L2 and C2. The both are inductively coupled and we have taken the final output of the circuit from the capacitor C2. To obtain high selectivity, why we are going for the double tuning? Because to obtain high selectivity, high gain and required bandwidth, double tuned voltage amplify a double tuned voltage amplifier circuit is shown. To obtain high selectivity, high gain and required bandwidth, double tuned voltage amplifier is used. In the circuit arrangement, it may be noted that all other circuit components such as biasing components, coupling component, coupling capacitor, emitter bypass capacitor are the same except collector circuit. Now this circuit consists of two tuned circuits, that is one L1 C1 and the collector in the collector and the other L2 C2 in the output. See the circuit, right? It is same. In the collector, circuit is connected to the L1 C1 by replacing the load resistor RL, and L2 C2 is connected across the output. These are magnetically coupled and are usually placed over ferrite rod. RS are used. Generally, the L1 and L2 are inductively coupled, but if you use the magnetically coupling concept, if you place the ferrite rod between these two, then they are magnetically coupled. And the circuit operation is in the signal to be amplified is applied at the input terminal through the coupling capacitor C in, right? This signal to be amplified, input signal which has to be amplified, is applied across the input. The resonant frequency of the tuner circuit L1 C1 is made equal to that of the signal by adjusting L1 or C1. Under these conditions, the tuner circuit offers very high impedance to the input signal. The tuning circuit, single tuned amplifier circuit concept. L1 C1 are selected such that the F0 is equal to 1 by 2 pi root L1 C1 is equal to the input signal frequency which has to be amplified, and as a result of this, a large output appears across the tuned circuit L1 C1. The output from this tuned circuit is inductively coupled to the L2 C2 tuned circuit. The double tuned voltage amplifiers are extensively used in intermediate frequency IF amplifiers in radio and television receivers. In radio and television receivers, If you see the block diagram, we have different tuned amplifiers. First the receiver circuit, then followed by a single tuned circuit, then followed by IF frequency circuit, then followed by power amplifiers. Like this we have different amplifiers in that application. For a particular block, that is IF block, intermediate frequency, we use double tuned voltage amplifiers. Now class C tuned amplifier circuit. In the first slide we have seen that tuned amplifiers. In the large signal tuned amplifiers can be obtained from class B and class C. Now we have to see the class C operation, in which the theta, that is the conducting angle, is less than 180. See the load line concept. Directly we are going to the concept of load line in this tuned amplifier circuit class C operation, where the Q point is below the x-axis. See, it is below VCC and VCE. If we draw the input signals and same output current and output voltage waveforms from the input waveforms, we are getting a clip. That means the already the negative portion, or half of the input signal is clipped off, because of the Q point is, if it is at the x-axis itself, the half of the input waveform will be vanished. If it is below the x-axis, means in the remaining whatever the half cycle we are getting, in that also we will get some portion will be clipped off. From the figure you can see that clearly collector current flow for less than 180 degrees. That is important. Collector current flow is for less than 180 degrees. Why? Because of this Q point selection. The amplifier is said to be class C amplifier if the Q point and the input signal are selected such that the output signal is obtained for less than a half cycle. For a full input cycle, input is full cycle, but we are getting the output for only less than the half of the cycle. Due to such a selection, the Q point transistor remains active for less than a half cycle. Hence only that much part is reproduced at the output. For remaining cycle of the input signal, transistor remains cut off and no signal is produced at the output. This is very basic, and we have already seen about the class A type and class B in the previous lecture. That's how the power amplifiers work actually. The current and voltage waveforms for a class C amplifier operation are shown in figure. Looking at the figure, it is apparent that the total angle during which the current flows is less than 180 degrees. It's not 1800, as you know, it is 180. This angle is called the conduction angle, that is theta. Now we have to see the operation of class C tuned amplifiers. This is a tuned amplifier, because in the load RL resistor is replaced with tuned circuit, and the transistor is operating in the class C mode. It's a power amplifier, that's why we use power transistor, and the Q point is selected such that the conduction angle for the collector current should be less than 180 degrees. Figure shows the class C tuned amplifier. Here a parallel resonant circuit acts as load impedance. As collector current flows for less than half a cycle, the collector current looks like a narrow pulses, as shown in figure 3.27b. See, collector current flows for less than 180 degrees. The continuous line is actually the less than 180 degrees. The dashed line, dotted line, completes the cycle. These dotted lines are clipped off. They are removed because of the selection of Q point below the x-axis. So these remaining portions, whatever we are getting at the output, that is less than 180 degrees waveforms, that is not even the complete half cycle itself. They look like the pulses. Figure shows the ideal collector emitter voltage in a class C transistor amplifier. In figure 3.27c, it may be noted that when narrow current pulses like these drive a high Q resonance circuit, the voltage across the circuit is almost a perfect sine wave. One very important advantage of class A operation is its high efficiency. Look at this point very carefully. It may be noted that when narrow current pulses like these drive a high Q resonant circuit, the voltage across the circuit is almost a perfect sine wave. So this type of phenomena occurs in class C operation where the transistor operates in less than 180 degrees, which are look like a narrow pulses, but as the output is a tuned circuit, the output voltage across the tuned circuit will look like a perfect sine wave because of the tuning circuit. And the class C power amplifier normally use RF power transistors, radio frequency power transistors. The operation case 1, when no AC input signal is applied, no collector current flows because the emitter diode base emitter junction is unbiased. As we know that when an AC signal is applied, clamping action takes place as shown in figure. The clamping action will takes place. The clamp circuit, generally, what do you mean by clamp circuit? It is a capacitor in parallel with the diode. These right, the voltage across the emitter diode varies between plus 0.7 volts during the positive peaks of input to about minus 2 am during the negative peaks of input signal. This means that conduction of transistor occurs only for a short period during the positive peaks of the signal. The result is the pulsed output, that is collector current waveform, is a train of narrow pulses. When this pulsed output is fed to the LC circuit, sine wave output is obtained. This can be easily explained since the pulse is narrow, inductor looks like high impedance and the capacitor like low impedance. Consequently, most of the current charges the capacitor as shown in figure. When the capacitor is fully charged, it will discharge through the coil and the load resistor, setting up oscillations just as an oscillator circuit does. Consequently, sine wave output is obtained. Right, because the pulsar signals, whatever we are getting at the output, because of the class C operation, are applied to a capacitor C1 and the emitter diode. The diode is from the transistor itself. Because of the base and emitter, they are actually work as a diode. So if you replace that circuit and redraw it as a capacitor in series with the diode, and we are taking the output across the diode, it acts like a clamping circuit. If we can remember the clamping circuit, the pulses will be shifted either above the x-axis or below the x-axis depending on the diode direction. As the diode has a cut-in voltage of 0.7 volts, so they are shifted somewhat to the below the x-axis, and these pulses will be applied across the load, that is L, in parallel with the capacitor. In this circuit, the pulses signals will charge the capacitor first, then after reaching the peak, that it will start discharging. The capacitor, whenever it starts discharging, the same current will flow through the inductor because of a loop. They are connected in parallel, right? So the capacitor, whatever it is, charging to the peak and starts discharging when it reaches to the peak, and going to the below, then the discharged current will charge the inductor. Please understood, because that's how the tuned circuit works actually. Because whenever the capacitor discharges, the discharge current will charge the inductor, and after certain time, whenever it reaches to the maximum, again the pulsar signal, and it will start decreasing the value. Then the inductor will start discharging. Inductors, whatever the stored energy will start discharging, which will result in the charging of capacitor. Because of the loop connection, this will happen, and as the time passes, these charging and discharging of the particular capacitor and inductors, the voltage, if you draw the voltage waveform with the time, then it will be a smooth curve we get as the same as sinusoidal wave, because the capacitor charges to the maximum and again start discharging, reaches to zero. The same current will flow through the inductor, which will be in negative direction and reaches to the negative maximum, and again it reaches to zero, and again the capacitor will start charging and reaches to maximum, then start zero, and again negative and zero. So there will be a production of smooth sine wave. So consequently, most of the current charges the capacitor as shown here. When the capacitor is fully charged, it will discharge through the coil and the load, just setting up oscillation just as oscillator circuit does. Consequently, since wave output is obtained, if only a single current pulse drives the LC circuit, we will get damped sine wave output. Right? If only single current pulse drives, we will get damped sine wave output. However, if a train of narrow pulses drive the LC circuit, we shall get undamped sine wave output, because in the input we are applying a continuous AC signal. If we apply only the pulse, single pulse, then we get a damped version of the sine wave. Only a single pulse, then we start decreasing and reaches to zero. That is if we apply only a single pulse, but we are applying the whole continuous wave, so we will get train of pulses, which results in the output sinusoidal smooth sinusoidal waveform. Typically, the conduction angle is much less than 180 degrees. The power dissipation of the transistor depends on the conduction angle. It increases when conduction angle increases. The conduction angle of class C is less than 180 degrees, so the power dissipation is less, and it increases with conduction angle. Next, we shall see the applications of tuned circuits. We will use these tuned circuits in AM or FM radios. As you know, these are practical applications. You would have already seen a particular FM radio in television receivers and transmitters. In oscillator circuits, it is generally used to make the damping factor as small as possible, or equivalently to increase the quality factor C, so Q, as much as possible. So in this today's topics, we have learned about these topics, which we will quickly revision because we have less time, about 5 to 6 minutes left with today's class. So instead of going to the next fresh topic, if we just revise the whatever the topics we discussed today, it will be very useful. Today we have seen about the classification of tuned amplifiers, that is small signal and large signal, depending on the size of the signal, that is power size, power value. And we have seen classification in the small signal tuned amplifiers. Again, it is single, double or staggered tuned because of the number of tuned circuits applies and what the signal frequency where we have chosen it to tune. And we have seen the frequency response curve of a typical tuned circuit. where we get the maximum gain at f0, that is resonant frequency, and the gain will decrease either to the left side or right side, that is above the f0 or below the f0 value. And the f0 is calculated, and the formula will we get is 1 by 2 pi root L C. And the resonant frequency, the impedance of the parallel resonant circuit is very high and decreases as the frequency changes above or below the resonant frequency. And the Q value, because Q is very important factor in case of tuned amplifiers, Q should be very high if you want the selection of a tuned frequency. Now we have seen the basic single tuned amplifier circuits, which is a similar to the basic amplifier, but the load resistor is replaced with a tank circuit, where tank circuit is a L, that is inductor in parallel with a capacitor, and the output is taken across the RL. And we have seen the operation of this particular circuit. With the inductive coupling we will get the output, and we can get the capacitive coupling also. Next we have seen about the double tuned amplifier circuit, in which the load RL is replaced with a single tune, and we have used the double tune here, L1 C1 and L2 C2, where L2 C2 is connected across the L1 C1 through magnetically coupling, concept of magnetically coupling. Why we are going for the double tune? Because of high selectivity, high gain, and required bandwidth. And we have seen the circuit operation of this particular double tuning, that is L1 C1 and L2 C2, and where we use this particular double tune amplifiers because it is used in intermediate frequency amplifiers in radio television. Next we have gone to the class C operation, class C tuned amplifier circuit, where class C means the conduction angle theta of the particular circuit is less than 180 degrees. And we have chosen the Q point that is below the x-axis, VC axis, but that is on the load line itself. If you observe the Q point and if you draw the output waveforms, current waveform and voltage waveform depending on the input pure sinusoidal wave, and by drawing the waveforms we can see the some portion, that is most of the second half, that is either positive half or negative half, is become zero, that it will not get in the output. Beside that we still get some of the portion of this remained half cycle is removed, again it is removed, and so because of that we get single, it's like a pure pulses, pure train of pulses. And if these pulses are applied to the capacitor and to the base emitter junction here, which will act as a diode, so this circuit will function as a clamping circuit. It's like a clamping circuit, and these pulses will be shifted to the particular voltage level, that is 0.7 in case of silicon practical value, and these are applied to the tuner circuit. Because of the charging and discharging, periodic charging and discharging of capacitor voltage and inductors current, we will get the output is a smooth sinusoidal waveform because of the input pulses we are getting from the class C operation of the circuit, right? And we have gone through the applications of this tuned circuits. Tomorrow we will discuss the next chapter, that is oscillators, in the tomorrow's topic. And if you have any doubts, please mail me at my mail id suresh akul 2001 and if you want to study gain in-depth knowledge in these topics, please refer the book Electronic Devices and Circuits by Jacob Millman and Hawkins. You can freely get the e-PDF from the internet. Just Google it and If you want to do the experiments by yourself, to the virtual labs, please be practice some of the MCQs for your competitive exams, coming competitive exams like ESET. That will be very very helpful. Though you have listened it, read it again and again, by practicing some of the questions itself, you will get different type of viewpoints, and in seeing those options in case of MCQs and drawing the circuit by yourself, you will get different questions. So why like this, why it has to be like this, then you'll study about it more, then you will realize, then you will understand it better than just listening to the video itself. So that is today's topic. Thank you, one and all. Closing the session now.